So far in our discussions of traveling waves, we saw that they can reflect, transmit, and interfere with each other. During these events, the frequency and the wavelength of the waves have remained constant, and the source of the waves have been stationary. But what if the source of the wave was moving? Consider a car driving past you with its horn on. When the car comes towards you, does the pitch of the siren sound high or low? What about after the car has passed you? Let's watch it again and notice the pitch of the siren as it comes towards you, then away from you. Notice that the pitch of the sound appeared higher when it was coming towards, then became lower as it moved away. So the pitch or the frequency of the sound seems to change with motion. We call this relationship the Doppler effect. The effect is named after Christian Doppler, an Austrian physicist who first proposed it in 1842. Here's how Sheldon Cooper from the Big Bang Theory describes it.
It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
According to Sheldon, the Doppler effect is the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. So if there's any motion between the source of the wave and someone observing that source, then the observer's perceived or apparent frequency of the wave will be different to what the frequency of the wave actually is. When we talk about relative motion between the source and the observer, it could mean either the source is moving, or the observer is moving, or both are moving. Let's first consider the case where the source of the wave is moving. In this case, the wave will be sound waves created by the jet plane flying by. The sound wave is visualized as expanding circles that represent wavefronts or regions of compression as the wavefront expands outwards. The frequency of the wave is constant, but you will notice that the wavefronts in front of the jet are much closer than the wavefronts behind the jet. To explain this effect, let's simplify the visualization and consider the jet plane as a point source that is moving with a speed vs to the right. The source creates a sound wave, and one of the wavefronts is shown as a blue ring. The wavefront spreads out in all directions with a wave speed equal to the product of its frequency and its wavelength. So after one period of time, the wavelength has moved a distance equal to its wavelength. At the same time, the source has moved a distance equal to its speed times the period and produces another wavefront. The second wavefront is closer to the first wavefront by a distance traveled by the source during this time. An observer in front of the source sees the wavefront as having a wavelength given by lambda prime, which is the wavelength of the wave minus the distance traveled by the source. The perceived wavelength of the wave is thus shorter than the true wavelength. This can be written as lambda prime being equal to lambda minus x. The wavelength, lambda, can be written in terms of its speed and frequency, and the distance traveled by the source, x, can be written in terms of its velocity multiplied by the period. Of course, the period is the inverse of the frequency. Since the speed of the wave does not change, then the apparent wavelength must cause an apparent frequency given by f prime. If we take the inverse of this equation, we can get f prime in the numerator. Multiplying v on both sides and taking f as a common factor on the right-hand side of the equation gives us the apparent frequency being equal to the real frequency of the wave multiplied by the speed of the wave divided by the difference between the speed of the wave and the speed of the source. So the ratio of the speeds in the bracket acts as a multiplier to the frequency. If the source was not moving and Vs is equal to 0, then the bracket would be V divided by V, or 1, and the apparent frequency is equal to the real frequency. In other words, there is no change in the frequency heard by the observer when the source is stationary, and that's what we would expect. But if the source was moving and Vs has a non-zero value, then the denominator in the bracket is less than the numerator, and the bracket will have a value greater than 1. So the apparent frequency will be greater than the real frequency. That is, the frequency increases as the speed of the source increases when the source is moving towards the observer. We hear this increase in frequency as an increase in the pitch of the sound. Now let's look at the case when the observer is behind the source of the wave, with the source moving away from the observer. Behind the source, the observer sees the wavefronts being further apart. This time, the apparent wavelength is longer than the true wavelength by the distance traveled by the source in one period of time. The distance traveled by the source can be written in terms of its speed as Vs multiplied by the period, or Vs divided by the frequency, since the frequency is the inverse of the period. Just like before, the wavelengths can be written in terms of their speeds and frequencies. Taking the inverse of the equation, then solving for the apparent frequency, we get the apparent frequency being equal to the real frequency of the wave multiplied by the speed of the wave divided by the sum of the speed of the wave and the speed of the source. So the ratio of the speeds in the bracket act as a multiplier to the frequency. If the source was not moving and Vs is equal to 0, then the bracket would be V divided by V, or 1, and the apparent frequency is equal to the true frequency. In other words, there is no change in the frequency heard by the observer when the source is stationary. And that's what we would expect. But if the source was moving and Vs has a non-zero value, then the denominator in the bracket is greater than the numerator, and the bracket will have a value less than 1. So the apparent frequency will be less than the real frequency. Thus, the frequency decreases as the speed of the source increases when the source is moving away from the observer. We hear this decrease in the frequency as a decrease in the pitch of the sound. A similar analysis can also be made, but this time with the source being stationary and the observer moving instead. When the observer moves towards the source, the wavefront hits the observer at a faster rate, so the relative speed of the wavefront increases and causes an increase in the apparent frequency heard by the observer. When the observer is moving away from the source, the wavefronts hit the observer at a slower rate. So the relative speed of the wave decreases and causes a decrease in the apparent frequency heard by the observer. A similar derivation for the apparent frequency gives the following formula for the case when the source is stationary and the observer is moving. When the observer is moving towards the stationary source, the frequency is increased by a factor equal to the amount given by the sum of the wave velocity v and the observer velocity Vo divided by the wave velocity. When the observer is moving away from the stationary source, the frequency is decreased by a factor equal to the amount given by the difference between the wave velocity v and the observer velocity Vo divided by the wave velocity. The four cases can be combined in one general formula for the Doppler effect, where f prime is the apparent frequency of the wave heard by the observer, f is the true frequency of the wave, v is the wave speed, Vo is the speed of the observer, and Vs is the speed of the source of the wave. The upper signs in the fraction represent cases where either the observer or the source are moving towards each other, and the lower signs represent cases where either the observer or the source are moving away from each other. If you've ever been booked for speeding in your car, you've probably experienced one of the applications of the Doppler effect. It's the principle used to determine car speed in radar guns. Another application of the Doppler effect is in astronomy, where the shift in the frequencies of light from distant stars can tell us how fast they are moving and in which direction from us. When a star is moving away from us, the frequency of the light decreases, causing an increase in the light wavelength towards the red end of the electromagnetic spectrum. We call this redshifting. Conversely, when the star is moving away from us, the frequency of the light increases and the wavelength shortens towards the blue end of the spectrum. Now for a few quizzes to test your understanding. In summary, the Doppler effect is the apparent change in the frequency of a wave caused by the relative motion between the source of the wave and the observer. This change in frequency is given by the following formula, where f prime is the apparent frequency of the wave heard by the observer, f is the true frequency of the wave, v is the wave speed, Vo is the speed of the observer, and Vs is the speed of the source of the wave. When the source or the observer are moving towards each other, then the apparent frequency is higher than the true frequency. When the source or the observer are moving away from each other, then the apparent frequency is lower than the true frequency.